Yeah, okay. So wait, I don't know like if Zach has learned about programming. So we're gonna like just go through like a few um basic concepts in programming, I guess. I only know Java. I'm not very good at coding, but I think I know some basic concepts in coding. Oh. So let's see. Wait, let me just share screen.
So we start with like different types of sorting. I think it's very interesting and how like try to visualize it and making sounds, which will be fun. I'll just make it play a little faster, like 2.
So I guess that's just like a demonstration of how sorting works in programming. I guess in like particular cases, I think it's pretty cool to visualize what it actually like looks like. And the red line symbolizes the scanner, and I'll use the whiteboard just to quickly go through. I guess like some basic stuff that I know about Java programming. So there are like different types of variable. So I'll just list some most common here. So like int, it's all integer. Like this is basically integers, and then it all has a range. But usually int covers most like whole numbers needed in programming. And then double. Double will basically represent um stuffs like 2.3 or 1.33, things like that. And then Boolean variables, which will just be true and false. And then if you want to store like a list of stuffs, you can use array and array list. Um, Array is usually like has a fixed number of elements, and then so it's like so it'll be relatively difficult, I guess, or like you need more steps to add an element to like a set number, a set array, but it's always easier to do it in an array list to add and delete stuffs. And also because of their properties, then array usually runs faster than an array list. Um, yeah, I guess these are the stuff that just come into mind that are often seen in programming. Sorry that there's noises outside my room, but and then we can go through like some common stuffs that you'll probably write. So one is conditional statements, I guess. So basically, it will look like if a condition one. I'm sorry, I need to go up and to just tell people So basically, if you have like if condition 1 is satisfied, so if this is true, then you will do blah blah blah. Like it will do something here, and then you can continue with else if, which is another condition, or you can just say else, and then you do blah blah blah. This is basically like conditional statements, and then loops. Loops, like there are several more common ones. Personally, I like to use for loops because it's just controllable. It usually like is like this, and then or I larger than the number, I plus plus or I minus minus, and then you will just in within this number, like within this num times of the loop, you will do like an action this number of times. And another way you can do is it doesn't really necessarily um, have a set number of doing the thing as you like calculated, but you can use a while something is true, and then you can just continue doing it, like doing an action repetitively until this condition becomes false to one loop. Both are fairly common and very useful in programming. Um, yeah, and so that's it for loops. So a little bit about algorithms. I don't know a lot about algorithms, but we're learning this year about genetic algorithms, which I think is interesting. Um, so if you had some experience in biology, that you know that is when you have like a genome that's fitting like that's ideal for the environment, then the species the individuals with that genome is likely to have a higher chance of reproducing, thus causing um, the more likelihood of that being to exist or to continue. So it's basically the same idea here. So for example, if we want to make uh, the, the program automatically writes hello world in this sense. Okay, so let's count. There are like 12 like places, or uh like if you put it in an array, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are basically 12 places that you can play with, I guess. And then when you think about it, if I just randomly generates stuffs, then it might be something like A, C, D, or something like you know, you can just fill in randomly, and by putting X, it's actually working because it's possible. um so if you have something like this, we can somehow figure out a way to measure the fitness of what the ideal result is by saying like, okay, so if A is and we just list A, B, C, D, E, F, G, um, H, I, J, all the way to Z, I guess. You can give a numerical number, and then you can always calculate the absolute value difference between the two. Um, and then you add the all 12 together, then you can get like a sense of how close the thing is, because when it's exactly the same, then it will be 0. So you want to be as close to 0 as possible. So if we have like a population of like these randomly selected stuffs, let's say like 200, and then we can always try to like select, for example, 100 that are like best and 100 that are not that good, like not like just relatively worst fit, and then we say that we can pair these two together, like the two elements within these 100 group individuals together to form like 50 parents. and they can give birth to two new individuals, so A and B, I guess. And within this process, there's also a probability of mutating. So A might be A mutated, and B will just be B. Because in any type of natural settings, that there will always be mutations. So you want to include that element as well, particularly when you have like a much more complex text task than this. And for B, what you can do is you can say, okay, I'm gonna randomly take a part from the first parent. So let's say like, let's see what I'm gonna, so parent one and parent two. Okay, so what you want to do is you can say, okay, I'm gonna take from this part to this part from parent one, and the second part from parent two, and that'll be okay. And then you can say like to make it simpler, then you can say, oh, the to the same place, like to the ends place, I guess. You can take the part from P2 and then mix this with P1. And theoretically, that if you do this um, for a time, for like enough times, then you can eventually reach this result as expected. So I can show the code in a second. I'm stop sharing now and just pull my code. Okay, so here's the code, and the most important part is just is this create new population. So when you think about it, the process, you're just from an old population, you're trying to create a new one, and then you want to find the one that will create the difference of zero. And when you look at so you can see that we created a new population, and as long as the whole thing is not filled, then you just keep choosing. And the chromosomes is just what I say, like the individuals in the stuff is. And then you have like parents making children, and also if there's a chance that it doesn't work, then the child, like the children will mutate, and you put in results. So let's just see what it will look like. Yeah, so let's just move it up. So at first you see that there's like just random chars, and then when you go a little bit uh later, then you can see it's getting closer and closer. And because the best fits are getting kept, and they have the chance to have children, then and steadily you will see that it will become closer and closer to hello world. So you see, like in this case, it's getting very close, and yeah, you will get hello world uh just by doing this, which is pretty cool. And some other stuff that you can see, I think a lot of stuffs that that like I'm talking about is just what you will learn from AP Computer Science with Travis. I did not know a lot about computer science, to be honest, but I can show some very cool stuff that we did in the class. Um, so for example, let's so in the class we did something like this, and it's which is pretty funny and interesting, I guess. You're just making interesting things like this, And I can also show something else, which is more practical and also um, a little bit reflectional, I guess, when you think about it. So let's see. Okay, so you should see this. Okay, so this is just an epidemic project that we did actually before the COVID begins. So if we think about it, that COVID-19 is followed the pattern SCIR, and we can see that we can say, let me make the cell size a little bit smaller. So this is for density 40, and if you have one infected into a density of 40 population, that you can see how it will spread basically in this trend. And the program automatically stops when there's no infected in the whole plane, I guess. And then for the orange ones, I guess it's vaccinated, and for the red ones, it's not vaccinated. And if we lower the density, which is what supposedly social distancing do, is lower density in a certain area and to create individual distances. And if we change density into 10, and if we put more infected in here, then you will see that the spread is relatively limited. So I guess it's a demonstration of why social distancing works. And you can do like things like putting in new stuffs in there, such as like common cold, malaria, and you can just still see how these spreads, which is pretty interesting. And so it's just a demonstration of how computer science and programs can be applied to real life situations, I guess. Um, that's pretty much for my part. Forrest, do you have anything for sorting that you can share?
Yeah, so let me see if I can. Okay, can you, Lingon, can you give me sharing permission?
Okay.
So, so this should be showing the sorting examples document. So, I'm going to go over how these different sorting algorithms work. So for bubble sort, what we do is that we look at the first two elements and we see that they're already sorted, so we don't do anything. But when we look at these two elements, they're not sorted, so we will move the 5 below the 1. Now looking at 5 and 6, they are sorted. Looking at 6 and 2, they're not sorted, so we switch them. And 6 and 4 are not sorted, so we switch them. So basically you look at consecutive pairs of elements, and then if they are sorted, you will leave them. If they're not, you will switch them. So doing this again, the 3 moves here, 3 does not displace 5, 5 moves there, and to there. And bubble sort is actually relatively slow because you do have to compare every pair of elements, and you also have to do a lot of switching. For selection sort is probably the one that comes to mind first when you're thinking of sorting. So basically what happens is that you go through the array or the list, you find the one that's the smallest, and that's going to be 1 in this case. And then you switch swap it to the beginning. So I put an extra slot here for temporary. So the 7 moves here, and now the 1 goes to the beginning. Checking all of these, you can see that 2 is the smallest, so it stays there. And this one also compares, I believe that this one also mostly compares almost every pair of elements, but it's slightly faster on average than bubble sort. So just completing this. And when you get close to the end, there's your elements to look at. So then after checking those, then you have the sorted list. Insertion sort is slightly faster than bubble sort and selection sort on average, I believe. So the way it works is that you start at the beginning and you slowly build your way up. So like you'll have 1 element sorted, and then 2 elements, 3 elements, 4 elements. You have all of those sorted. And the way it works is that you start with 3. 3 just by itself would already be sorted. 3, 6 would already be sorted, but when you add the 2, it's not sorted. So what happens is that you test 2 against 6, and 2 is less than 6, and then you test against 3, 2 is less than 3. So basically, when you have the sorted part, you move the first non-sorted element to where it should, between the 2 numbers where it would be. So 7 goes between 6 and 8, 1 goes to the beginning, 4 goes between 3 and 6, 9 stays, and 5 goes between 4 and 6. So insertion sort is slightly faster than these other ones because on average you're only going to move it to about halfway through the sorted part, while for bubble sort you have to compare every pair, and for selection sort it's basically the same. For insertion sort, you're only comparing it, you're doing about half as many comparisons. So insertion sort is usually slightly faster. So, okay, so I have put the spare ones down there. I'll cover merge sort first. So we didn't talk much about how fast programs run, but there's something called big O notation, and these ones are all O of n squared. Quicksort can be O of n squared, can be O of n. I mean O of n log n. Merge sort is always O of n log n. So the way that this works is that you separate, so you separate the array into many parts. And I put 8 here because 8 is convenient, but you could do it with other numbers. It's just that it might not be perfectly even, but it doesn't really affect the result as much. So the important thing about merge sort is merging. So if you look at this, you see that 2 is less than 4, so 2 is going to go before 4. And then that. So now we have length 2 lists sorted. Now what we do is that we combine these ones and we look at these two elements and we see 2 is smaller than 6. And then we put the 2 in a different array. Now we look at 4 and 6. 4 is less than 6. And since we ran out of elements in this array, we can just move this over. Looking here, 1 is less than 5, and 3 is less than 5. So you put that there. Now we have length 4 lists that are both sorted, and we do the merge process again. So 1 is less 1. So the first one, between 1 and 2, 1 is smaller. 2 and 3, 2 is smaller. 4 and 3, 3 is smaller. And so on. And so once you finish the merge process, then you output this array as the sorted. So I said that merge sort is O of n log n, which means that on really large scales, it's much more efficient. It's going to be more efficient than bubble sort, selection sort, and insertion sort. So quicksort is there's different ways to do quicksort, but the idea is that you pick one of the elements and you move everything that would go before it and everything that would go after it after. So you can pick any element. I usually just, when doing it manually, I usually just pick the first one. You can now the reason that quicksort can sometimes be not as good as merge sort is because if it's already in sorted order and you pick the first element, then it's not going to change then you'll get really uneven partitions. Like if you pick the last or first element as your pivot, then that's not going to help at all. So we're going to try to sort these alphabetically. So Washington, so this goes after, this also goes after. So we're only going to care about whether it's before or after. We're not going to like compare these two yet. This is also after. These are all after. In Rafalak goes before. Gassy Chut says goes before. You can put these in any order that you want, but I'm just going to try to be consistent. Okay, so hopefully everything before the pivot is ahead of it in the alphabet, and everything after is below it in the alphabet. So now that that guarantees that Pennsylvania is in the right spot. In the final sorted position, it will be in the right spot. So now that we have reduced it to smaller arrays, we just repeat the process. And I think that for this one, it's not as helpful. So I'm pretty sure that's how it works. So as you can see, for this one, in Rafalak as a pivot, it only moved Adanak above it, and it left a really uneven uneven divide, and that can sometimes happen with quicksort, and that's how quicksort sometimes can be O of n squared. So since this is just by itself, it's definitely sorted. So now we use this one, and I think this is an example of where it gives the last one. And you just keep doing this until you just keep picking the pivots until, like, the ones that are not pivots, you want the, or I think that it's best if there's one space between them, and so it would be sorted. I'm pretty sure that's how it works. So now that we sorted the first part of the array, now we sort this part using the same process. So Washington. And I think all of these go before Washington. And here's another example of a not great pivot. New York, I think this one goes ahead. L. So I chose so as you can tell, this is a larger set, and quicksort is faster or for really large sets, really large arrays. Okay, so like if I were to do this using bubble sort, it would be much slower. Even selection sort would probably also be slower. And you just keep doing this. So as you can tell, like doing this by hand, it seems slow, but if you did this with a computer, it would be much quicker and much faster than some of the other possible sorting algorithms. So like when I'm sorting larger arrays, it's much better to use quicksort than bubble sort or other ones. And you can analyze, there are faster sorts than quicksort for extremely large sets or arrays, including radix sort. Radix sort, you look at the last digit and then the second to last digit, and you just put them into the groups that have the same last digit, same second to last digit, and that eventually gets sorted. That one will run basically as O of n. So that can be extremely quick so that will be very quick for that'll be quick for extremely large arrays, but for small ones, these three, they're okay. For medium-sized ones, you probably want to use these two. If it's extremely large, then radix sort might work better. So quicksort can sometimes be better than merge sort, sometimes it's not. Does anyone have any questions on those sorts?
Okay. It's 12:28. We could just finish right here.
Yeah, I think we'll have assembling next. So like in
Yeah.
2 minutes. So I guess we gotta go.
Thank you, guys.
Bye. Have a good weekend.
Uh,
Bye.